In this video, we are going to look at sound intensity and its corresponding receptive trait of loudness. We're going to attempt to answer the question why sound seems to get quieter the further away you are. So you have actually seen the equation for intensity before. Back in the energy unit, we calculated the intensity of electromagnetic energy leaving the sun, where I have intensity equals power divided by area. And since the sun emitted electromagnetic radiation in a spherical pattern, the area could be corresponding to the area of the sphere, 4 pi r squared. So why can we use the same equation here? Well, sound, remember, is emitted in longitudinal waves that leave the sound source also in a spherical manner. And the wave fronts, as they get further and further and further away from the sound source, end up looking more and more and more like plane waves, where they go from being curved to being almost straight. So the distance that the wavefront is from the sound source actually will increase, and therefore the intensity will decrease. And so if you were to measure this in terms of a sound wave, the amplitude of each peak would decrease over time because you are getting further and further and further away from the sound source. So how does this look in terms of an actual diagram? Here's my source of my sound in the center here. And as time moves on, that wavefront moves further and further and further away from the power source, in this case, the sound source. So as I increase the distance away from the source, or increase the radius, I will end up decreasing the intensity. And I'm going to end up doing that by a power of r squared. So if I end up doubling the radius, I will end up decreasing the intensity by a power of 4. If I triple the radius, I'll end up decreasing the intensity by a power of 9. And you can see that clearly in this diagram here because they have broken up the wavefronts into area segments so you can see how the intensity actually decreases. So here's that equation again. Intensity of sound in this particular case is the power of the sound, or the disturbance, the power of the disturbance that originally created that sound, divided by the area. And since the sound wave is leaving in a spherical manner, area can be found by 4 pi r squared. So please write this equation down in your notebook. Keep that, and you are now going to be able to figure out the intensity of any sound if you know the distance or you know the power. Now, remember that sound is only received if you've got a receptor. So you can have a longitudinal compression and rarefaction wave that has some amount of intensity, but in order for that sound to have some sort of volume to it, we have to have a receptor. So the loudness of the sound is only paired up with this term if we've got a receptor of that longitudinal compression wave. So loudness is defined as a perceived value of intensity of a sound wave. So again, if you have an eardrum present, you can register that intensity of that wave as loudness. Relative intensity is the comparison between the intensity of a sound to the threshold of hearing. Remember that humans have a range that they can hear sound within. The frequency at which humans can hear sound is from 100 to 10,000 hertz. We have figured out by doing a lot of science and a lot of mathematics that humans tend to perceive the loudness of a sound in increments of powers of 10. That's why we get the term decibel. Decibel, we can break that term down into deci meaning 10, bell meaning a bell that you can ring. So the term decibels as a measurement of loudness literally means how many increments of 10 bells. Here is a chart to look at in order to compare frequency to intensity or loudness. So on the x-axis, we've got frequency of a sound. On the y-axis, we have intensity level in decibels, meaning how we perceive the loudness of a sound. And this border right on the bottom here is the threshold of hearing. So for instance, if I have a frequency of 100 hertz and an intensity of, let's say 38 decibels, you can barely hear that sound. Everything in the pink region is stuff that we can hear. Everything in the hot pink region is usually the intensity versus frequency of music that we listen to. And everything in the center is the frequency versus intensity regions where we can hear people talk. At the very top here is the threshold of pain. So anything over 130 decibels and over 20,000 hertz to under 20 hertz actually can cause pain in human beings as they're listening to that sound. Here is a table of common sound levels and decibels and their corresponding intensities. So starting at the bottom here, threshold of hearing is at 0 decibels, and the intensity of that sound is 10 to the negative 12 watts per meter squared. As I increase in increments of 10 decibels, I end up increasing the intensity and the ability to hear that particular sound. So rustling leaves are down here at 10 decibels. The intensity that corresponds with this is 1 times 10 to the negative 11th. And I can go all the way up to a nearby jet airplane. Nearby jet airplane has a sound level of 150 decibels. That's why when you go to the airport, you'll always see the flight control people on the runway have headphones on. And that corresponding intensity is 1,000 watts per meter squared, pretty intense. So if you look here, rock concert, this is really interesting. Sound level at a typical rock concert, depending on where you're standing or how close you are to the stage, is 120 decibels. And we have that labeled with an intensity of 1 watt per meter squared. So that is the point where you actually start to experience pain as you're listening to these sounds in terms of loudness. So short video today. I think that you are now ready to do page 415, numbers 1 through 5. And then you can move on and revisit the video standing waves and harmonics. And then we will talk on Wednesday or Thursday about resonance.